Okay, my outstanding friends, I promised you a geek fest, and you shall have a geek fest. We're going to start by a quick introduction to him saying gravity is a lie, light speed is slow, nothing is real, the universe is electric. Some of that I agree with, some I don't. But let's dig into this. But I'm going to show you about light and about heat and about gravity and about the ionosphere and the temperatures in the ionosphere and how light collects in our atmosphere and how light reacts with everything in our atmosphere and everything in nature. We have to start right from the beginning. You got to get to dipole electron flood theory before you can understand anything. Really, it's as simple as that. And dipole electron flood theory is the most simple solution to this extremely complex question that's been going on for hundreds of years. What is matter made out of? It's made out of dipole electrons. Light is not only bright, brilliant, and glowing, and hot and burning, it's got mass. They say no, photons don't have mass. Incorrect. Photons have mass. Just so you know, this is this Majorna and Dirac neutrinos. They're saying matter, antimatter. No. This is the white particle, which is not has no matter. It's no mass to it. It glows like hell and burns. This is the matter. So they got that backwards. But they are connected just like that, just like I showed you. And that is what I call a dipole electron. That's what a dipole electron is. And two of them back to back make a photon. The photon comes through the light. The light photon comes through the air, and everything in front of it, it excites all these little particles, and they have to get the hell out of the way. And it pushes through, and eventually it gets sucked through the venturi here, and it literally explodes. The white part explodes from the black. That's why these fields are showing up here. They're here. You can't see them. This one's showing up because it's getting sucked into the field. These are showing up because they're getting slammed back. This is literally a subatomic nuclear explosion. These particles are part of the nucleuses. They're part of the smallest particles exist, and they are broken apart right there. It's broke. This is when they're not broken. You see that? That's how they came into the venturi, just like that. At the venturi, they smashed it to bits, and the white just separated from the black. That is, it's fission and fusion. There's no other way to look at it. No other way to look at that at all. All right, it came in that box configuration. The black, the white, the black, the white. Boom! The black just stays back, and the white comes through as complete white. And then it rejoins the black again back here. This entanglement thing they're talking about from the other side of the universe, that's crazy. These particles are entangled, yes, but they re-entangle instantaneously. Okay, my friends, this is going to be fun. This is going to be a geek fest. We're going to look at how motors work, how generators work. I can show you in these little tiny motors. I've got them taken apart here. We'll be able to see inside what the brush box is, how the fields work, and all of that stuff. But a lot of people don't have a good grasp on just ordinary things that they work with every day. Little motors, little this, little that, electricity, static, lightning. Even like this Crookes radiometer. 150 years ago this was invented. And still today they don't know how it works. We're going to look into this, and we're going to see if we can figure this out, because I think we might be able to. You got to look at all the variables and then decide, how did this change and what changed it? Because heat will make this thing go in this direction. Cold will make it go in that direction. I'm not kidding. You shine a light on here and it pushes the black around this way. You shine the light on the white and it sucks the white towards it. it's affected by cold and heat and light, and nobody can come up with a solution to why it does it. They call it transferation of heat, thermal transpiration, which they just think something gets hotter and gives off energy and makes a push. Well, I don't see that as being accurate, because as I will show you, light, the brilliant part of light, is the energy part. That's got the energy, but it doesn't have any mass. But in the normal world, whenever you have a bright light, attached to that light, even though it's bright and it's white, it has a black particle, and it's tightly attached. And you cannot pull them apart unless you put them through an accelerator like we did, or through a nuclear collider like they do at CERN, Fermilab, and so forth. They smash together. We forced our particles, which were started with light, into a venturi so small that only the white could come through. That's how we separated the black from the white. They separate the black from the white by hitting them head on, and they just get nothing but debris. And they see the black and they see the white, and they say, wow, those are the tiniest particles we've ever seen. We see them regularly, but all they know is they're the tiniest particles. Well, we know they're a part of light because I've shown this. And this is dipole electron flood theory. You look it up. AI says, if I'm right, which I am, I can guarantee you I'm right about this, because you'll see I'm right. If I am right, it changes everything in physics. Basically, that's what they say, fundamental reshift of everything in physics and chemistry. So don't forget, this is the unknown particles. This is different than a Higgs, but it's part of a Higgs. So what does that tell you? I think I understand this, and it's really, it makes sense when you do understand it, but in order to understand it, you have to understand dipole electron flood theory. And it makes total sense once you understand it, but it makes no sense whatsoever unless you understand it. Okay, I'm going to tell you right now, I, Roger Spur, Mudfossil University, understand quantum physics. Now let's see what they understand at Yale. This is Professor Shankar. He's a nice guy, and he's going to be honest. Now listen to what he has to say.
This is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now I'm the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So,
unfortunately, he's right. They have to say what they're told to say, whether it's right or wrong. And I've tried to communicate with Professor Shankar. I haven't gotten, there was no response. And they can't respond to me, because I changed things, and I have the evidence, and I'll show you right now. And he's right, nobody does understand it. Feynman didn't understand, nobody does. And they don't understand it today, because they have to go by Einstein's rule of c square and light speed and all of that nonsense. It's just nonsense. Okay, my friends, stay with me. This is going to be a geek fest. I love experimenting and trying to figure out how magnetism works, electricity, all that stuff. And I've done it for my whole life. So, and I've kept up with things, and I started with atomic theory in 1968 when I went in the Army, and I worked on Nike Hercules missiles and so forth, in missile sites, and I took a great interest. Anyway, I went on to take that in college and found out that there was no appetite for any discussion other than what the professors told you to say. If you even spoke up, they just crushed you, and that's what they tried to do to me. I fortunately won, but just that one little battle, you can't win the war. So I got out of that and started my own business. But it was in electronics, and it was fun, and it was successful. So I was glad to get out of that, because there's no wiggle room there. You just do what you're told to say, or they really literally can destroy your life. I'm serious. They can destroy your life. Just like that, just by saying, you didn't say what I told you to say. Because believe me, I didn't. And that's what they tried to crush me, and I won. And I forced my professor to give me an A, because I knew more than he did. And he knew I knew more than he did. And he wouldn't give me an A. He said, no, the best I'm going to give you is a B+. I said, no, you're not going to give me an A. I said, other than that, I'm going to go against you, and we're going to figure out the dipole molecular moment of some polar molecule. I just threw it out on the spot. And he said, all right, I'll give it the A. And he was bad. The guy was no good. Absolutely terrible. But I found that 100% of the time. 100%. That's why everything's stagnated. It's just nothing happens in science anymore, because it's an echo chamber. They use peer review to keep you from saying anything that they don't want you to say. They say, well, we don't want them to say that because we don't want them to say it. We're a bunch of bullies that can tell them you can't publish that. You say, why can't I publish it? Why can't I put it in front of people? Because we don't want you to say it. You're going to confuse them. I said, no, I'm not. I'm going to present them an alternative. I'm not trying to confuse anybody. I'm not trying to hurt anybody. And when I actually said that one time, I'm not trying to hurt anybody, they sent the police. They said, what are you not trying to hurt anybody? I said, no. I said, no. They didn't send them here. They called me, and they said, basically, they were saying I was threatening people. I said, I'm not threatening anybody. I said, I don't want to hurt their reputation or hurt their career, or there's a lot of ways to hurt somebody. That would come over and beat them up. And that's just, they came after me like that. That's 10, 12, more than that years ago. And I found out then, if you stand up and speak, you're in trouble. And because it wasn't just the police, it was the lawyers too. Because I started to put it on the internet about how I was being treated by academia, and it literally crushed everything I did. So that's water way over the dam. But it's certainly time now to start to understand that, not looking at what is obvious in front of your face. It's just not science. Not science. It's PhDolia, where you can't see what's in front of your face, and you just arrogantly deny it. No. Oh, I'm highly educated, and you are not. Plus, I have a bow tie. Okay, my outstanding friends, this is going to be really interesting. I am going to do the Schumann resonance frequencies, which nobody understands. And before I even do that, I'm going to talk about this guy here, Feynman. He was the big physics top guy. Now let me show you what they have to say about him at Yale, and about what they understand about quantum at Yale. Okay, my outstanding friends, this is going to be great. I love this stuff. And this is a discovery about the Schumann resonance frequencies that surround the Earth. And there's a certain hertz, and a hertz means how many cycles per second. It's push to shove, how many times per second. And Earth has that rhythmic heartbeat, they claim, of a certain frequency, which is somewhere between 7 and 8 hertz times per second. And it just keeps going forever. And it just, now, there are things that affect that though. Just like there are things when we run and jump and do all that stuff, we have added more energy into our system, and our heart gets going faster. Well, the same thing here happens to Earth. Well, what would do that to the Earth to make it think that it had to react like that? I will show you why, and we'll also explain what the experts' opinion, and it's wrong, I can tell you that right now, of what creates the Schumann resonance. They're partially right and completely wrong. What creates the resonance frequencies is capacitive discharge. Capacitance means you absorb a bunch of energy and then you discharge it. And then you absorb it and then you discharge it. And then that's creates this frequency. And I'll explain why we absorb it, why we discharge it. And it also helps to explain global warming. It completely validates dipole electron flood theory. We're going to talk about the ionosphere, which is the region in space that is out here that reacts with all the soup that's in space. And it is a soup of electrons, dipole electrons, really. It's light, it's particles, it's dust, it's meteorites, it's everything. There's all kinds of stuff out there. There's not nothing out there. There is all kinds of stuff out there. And that is going to affect, absolutely no question whatsoever, the speed of light. And we can also look at it as the frequencies of pulsation sort of diminish over the course of a distance. Because I have shots of this that show these magnetic fields emanating in space, all dipoles. We're going to look at that right now, and then we're going to jump into this kind of deep, the resonance. And I can explain to you, it's really very simple, but you have to understand dipole electron flood theory. And you have to understand the temperatures of the layers of the atmosphere. It's thousands and thousands of degrees way out here, thousands. On Earth it's 100. Why is it thousands out here? Well, I know why, and you will too. Okay, I'm certain you know who Tesla was. Now, what did he say and what was his big proclamations? Well, Tesla's famous quote was, "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration." And then in quotation, it says, highlights the interconnectedness of these concepts. He believed that everything in the universe, from the smallest particles to the largest objects, vibrate at a specific frequency, and understanding these vibrations is key to understanding reality. Well, that's a yes and a no in my world. Now, let's just look at the one thing he has to say that we're going to look deeply into. We're talking about hertz, which is cycles per second. How many cycles? So a cycle is it pushes this way and pushes that way. That's a cycle. Now, resonant frequencies is what we're going to be looking into. Remember this, resonant frequencies. Not just any frequency, resonant frequencies, meaning they vibrate most effectively at exactly certain frequencies. Most effectively. Well, effectively in what case? For the most amount of energy. The most amount of energy at a certain frequency. Okay, my friends, another shocker du jour. You've probably heard of the Schumann resonance frequencies. Maybe you have, maybe you haven't. We'll talk about it. This is an article this Dr. Polak did called Geomagnetic Fields and Schumann Resonances, showing the fields that surround the Earth and the resonances, and his claim of how these resonances are set up. What causes these pulsations, these different frequencies? And there's a certain pulsation that the Earth has. It's like a heartbeat, they say, and it pulses at approximately 7.5, 7.83, something like that, vibrations per second. Those are called hertz. 7.5, 7.8, right in that area. Now, they are not consistent. They are not always the same rate of pulsation. Why? What would change that? This is what I look at is, explain to me why they're not the same all the time. Now, their mainstream impression of this is that it's all related to electrical discharge of lightning. Now, I don't disagree with that. However, it's a bounce from layer to layer to layer to the earth, and it's a capacitive discharge. All right, capacitance means it grows the capacity up and boom, it discharges. It can only get to a certain point and then it wants to discharge because it's still getting filled up, and it discharges, pulses, and that's how it happens. Now, I'm going to try to explain this to you very simply, because it is simple. I have a little drawing I did to show you the interaction between the Earth and the Sun and all of the particles that are in space. And light, they're particles, and they have mass. They are energetic. That's what's hitting our outer atmosphere, causing it to be 3,000 degrees almost. So anyway, I'm not putting anybody down or anything, because nobody knows. Nobody understands what's going on here until you understand dipole electron flood theory. Now, the Earth has its own magnetic fields produced primarily by fluxes in the molten metal in the outer core of the planet. I totally disagree with that 100%. It's produced by the scrubbing of these particles in the outer edge against all the particles that are in space, because space is saturated with light. And light is nothing more than electrons. And so we're scrubbing through those electron fields, creating a huge amount of raw electrons. They say it's almost a vacuum there. It's not almost a vacuum. It's saturated with the white part of particles, which have no mass. They're they're white. It's not a vacuum. They are the particles that you never see because they're being scrubbed off of the dark part. Okay, my friends, I think I can show this very simply, actually. This is the Sun, and this is the Earth. Now, of course, they're not obviously close, and the Earth is much smaller than the Sun and so forth. However, this is the corona. Right out here. You see these OH minuses? You got OH minuses here. OH is the lightest gases, basically. And the minuses mean they're ions. They're ion hydrogens and oxygens. Now, that means that they either don't have enough, well, they're negative, so they just don't, they're missing their electrons, or they have extra electrons. What happens is, as the light comes out of here, it's in packets of light, which are the positive and negative little black and whites. When they hit our atmosphere, the white particles smash with the other white particles, and I believe the black just keeps right on coming. So you end up with a zone here they think is just nothing. It's a vacuum, but it's not. It's just the white. That's why it's so hot, because it's just the white. But without the black, the white just doesn't migrate into you. It's got something to do with the black, and that also has something to do with this right here, Crookes radiometer, because this also is in almost a vacuum, as is this. That has to be in a vacuum to do what it does. And when you shine the light on it, it does things that nobody can explain. I think I can explain it with a dipole electron flood theory. Because this not only works on light, it works on hot and cold. Cold makes it go this way. Hot makes it go the other direction. That's all. And underneath this outside layer, which is up to it's around 5,000 degrees. 5,000 degrees where these things scrub each other. Just below it is the dipole part, is minus 100 and something degrees. That's ridiculous. The difference in temperature is unbelievable. And then you get to the point where it creates these huge balls of ice because you've got condensation below that. Out there, you really don't have any gases to speak of. Well, you do have gases, but they're so thin that it's almost exclusively the electrons. And the electrons have no weight, and they just you don't even realize they're there, but they're so energetic that it's 5,000 degrees. So this is another mystery. Nobody can explain why it's so hot out here and why it's so hot out here. The sun is 10,000 degrees on the surface. Out here it's millions. How did it get from here to millions out here? How would it increase its temperature leaving here? You'd think it would be decreasing, but no. All of a sudden it hits out here and it's millions, and then it drops right off again. That's because it's scrubbing through space the same as we are. And we are scrubbing this zone, creating 5,000 degrees. And then right below it gets very cold. And on the Earth it's 100 degrees. It's 10,000 here, millions out there. That is because we're both scrubbing through space. And the space is just saturated with light. I mean, light comes from everywhere. I mean, it's just not deniable. This is a solar eclipse. We don't see this every day, but this is what's happening. The sun is behind the disk of the moon. All of this is particles of light. They're particles of light and ions and molecules and gases and who knows what. But they're going out and you don't see them because you're blinded by the light. You can't look into the sun and see all those particles. The only way we could do it is get that solar eclipse like this. You see that red spot, red spot, red spot? To me, the sun is turning this way, making more energy in these three spots and bigger energetic fields. They create a field as they spin, and this is the trailing edge. So it's going this way and headed that way. That's the way I take this picture. And of course, that's the moon. Again, trailing off particles. And we have to plow through those particles. They call that the solar, I forget what they call it. It's this solar storm or something. Solar wind, that's right. But now, here's what's happening. This is my little doodle here that I drew. Now, here's what's going on. We know from the Dipole Electron Flood Theory, we can see the particles, and some of them spin really fast, and some of them spin fairly slow. But they are spinning just like this. Coming from the sun, thrown out from the sun. If they're really fast buzzers, they're way down here, and they're spinning like crazy. And these are the ones that hit and make cosmic radiation. They make all the real energetic particles and smash into our layer out there, which is called our ionosphere, right at the very edge of space. Out there is just more particles. We got to get through them. Now, the moon radiates. It doesn't glow itself. It radiates back from what the sun's hitting it with. So you only get a certain amount of color. You can't get the real bright colors from the sun, from the moon. Now, these you can get from the very small, low frequency colors up to the extremely fast, high energy particles, which are the fast spinner. The closer they are together means the more interference between each field. You see that? If they're way apart, they're just lazy. They're not pushing each other. They're saying, yeah, just keep going. Have a nice day. Yeah. Well, when they're this close together, say, get out of the way. And they just get boom. Of course, they're spinning at the same time. And that's the difference between red and blue and green. Well, green being in the middle. Now, so here's the corona, millions of degrees. The sun, 10,000. Here's the Earth, 100-ish. Way out here, up to 5,000 degrees. There is no other explanation. We are scrubbing through the universe. All right, I don't want to make this too complicated. It freaks people out, but I'm going to try to explain these different fields that they're showing. And we found these fields just using a cell phone. All right, with an app, and I didn't do this. I got this from somebody, and I don't think he wants to be involved, but this is the fields that are in space, and these are the kind of things that are out there. I don't know what the hell's going on with all these little dots, But something's going on with them. Now, the reason you see all those little tiny spots around it, those, I believe, are pixels in the cell phone. All right, so I don't think they represent anything special. I don't know. But I see them, they're all on the same plane, more or less. And they're the little dots, and that's what pixels are made out of, is little dots. Now, and again, I didn't do this, so I don't know exactly how it was done, what kind of a phone, what kind of an app. But this was, I have a bunch of these different pictures from New Zealand. And you can see the fields, and you can see how they're really tight. And then eventually they taper off into nothing. They're done. You see? That's the same field. This is the moon. This is the moon. The moon is not giving off any field at all because it's not spinning. Spinning with an atmosphere is what creates the scrub, which creates the buildup of the field and the discharge, and the buildup and the discharge. That's what the Schumann resonance is. You don't spin, you don't charge. It's pushing against light, turning the light blue, but it's not charging up. And the moon is being pushed in this direction, you know, whatever. The moon doesn't spin, so it's just moving in that direction, rubbing into the light that isn't shown up as light. It's just sort of out there until it crushes it and pushes it from the, you know, up here into the blue spectrum where you can see it. That's the moon crushing the light, and the light having nowhere to go, collecting up here and then trailing off the edge. And it gets, as it collects more and more, it gets brighter and brighter and bluer and bluer. That's why the very tip is out here. It's not flat. Now you see this? I'm not sure who this was from. It's one of the major labs. And they're showing a white particle here and a dark particle here and the entangled fields. That's not too far. But I don't, at this point, all I can determine from this is the white hates the other whites. They will not get close to each other. When they get into a region next to each other, they oppose each other. The black one is extremely attractive to the white. Now, whether I know the white wants to go to the black, because the black is ground and stationary. The white is where you feed the particle in. It goes through the thing, through the motor, turns the motor, and ends up going into ground. So the white is attracted to the black. The black, it wants to be with the white, but it wants to be inside a ball of white. In other words, this is an atom, specifically a hydrogen, which means it's one proton. Inside that proton, though, is this, the dark part. We've never seen it. You're never going to see that dark part, ever, until you smash these into their tiniest components, which we did, and Fermilab did, and CERN does. They see the same particles we see. All right, this is Fermilab. This is right from Fermilab. There's their black particle. There's our black particle. There's their glowy particle. There's our glowy particle. They attach together and they make what's called a Dirac neutrino, which is the two trino. Di means two. Dirac neutrino. This is the muon neutrino. That's the electron neutrino. I agree with that 100%. We found them here in light. They found them from crashing huge particles and making a mess. We saw them coming through as light particles with the glowy edge, exactly like they said at Fermilab, and the glowy little particles. And these can get big and small, and they have no mass. I just don't know what to say about that. But I can tell you what: if you take two magnets and you push them, you know, there's going to be they won't go together. I can't get them to go together. It feels like there's a wall right there. Watch. Can you see down here? Yes, you can. Watch. Whenever I come close to there, it takes off. Now that's interesting. Wow. Wow, this magnet broke. And I taped it together because it seemed to be correct in that orientation. But did you just see what happened? I come up against this and it pushes. But if I turn it this way, it attracts. Now, I have another one. I thought I did. Maybe. Oh, yeah, here it is. This won't do that. This one here will not do that. Let's see what happens. Now I got 3 of them in a row. Whoops. Now watch this. These 2 won't do that. I can attract them, but once I go to the other side, it pushes from there, it pushes from there, it pushes. It doesn't matter where I go. They push everywhere. Ooh, this is very interesting. Because this broke in half, and I noticed they didn't want to go back together when they were on the right side, so I tipped one over and put it, and they snapped back together. And now we got 2 magnets in the same magnet. That one snaps together. And that one pushes apart. And that one pushes apart. This is all crazy stuff. Magnetism is very interesting. And these neodymium magnets are very breakable. Now, what we did was we took these light particles, put them through a venturi, which is right here. And the white separated from the black. It's called electron neutrino showers. The electron showers, the white cones. And the black is the muon neutrino. And here it is right there. And that white has no mass to it at all. There's no mass to the white. That's why they think there's a complete vacuum around the space. It's not. It's saturated with these white particles. That's where the white hits the white. All right, that's where the white hits the white. The white coming from the sun hits the white in our atmosphere out here as it scrubs through space. And all it leaves there is the white. The black must keep coming right through. And I think the Earth is made of it's made of dark matter because that's the only thing that has mass. The Earth is made out of dark matter. It's the only thing that has mass as far as I know. So we're made out of dark matter, my friends. The white particles, there's no mass to it, none, 0. A lot of energy, no mass. Just so you know, this is this Majorna and Dirac neutrinos. They're saying matter, antimatter, no. This is the white particle, which has no matter. It's no mass to it. It glows like hell and it burns. This is the matter. So they got that backwards. But they are connected just like that, just like I showed you. And that is what I call a dipole electron. That's what a dipole electron is. And 2 of them back to back make a photon. The photon comes through the light photon comes through the air, and everything in front of it excites all these little particles, and they have to get the hell out of the way. And it pushes through, and eventually it gets sucked through the venturi here, and it literally explodes. The white part explodes from the black. That's why these fields are showing up here. They're here, you can't see them. This one's showing up because it's getting sucked into the field. These are showing up because they're getting slammed back. This is literally a subatomic nuclear explosion. These particles are part of the nucleus. They're part of the smallest particles exist, and they are broken apart right there. It's broke. This is when they're not broken. You see that? That's how they came into the venturi, just like that. I mean, at the venturi, they smashed it to bits, and the white just separated from the black. That is, it's fission and fusion. There's no other way to look at it. No other way to look at that at all. All right, it came in that box configuration. The black, the white, the black, the white. Boom! The black just stays back, and the white comes through as complete white. And then it rejoins the black again back here. This entanglement thing they're talking about from the other side of the universe, that's crazy. These particles are entangled, yes, but they re-entangle instantaneously. This goes so far beyond cool, it's amazing. Again, Rod Warren did these experiments. He's over in Australia, and I don't think he wants to be involved. I I haven't heard from him in years. Anyway, this is the explosion at the Venturi. We're watching that wave come this way. You see all these little, very, very close lines? Those are the pulsation coming through the Venturi, and then the black particle is here. The black is the pusher. The black pushes the white. The white has no mass. You need the black to push the white. Now, the only reason we had white coming through the Venturi before is because it kept slapping at the Venturi and spitting only the white out. Now we got white and black. This one's tuned a little wider, and it's letting both come through, not equally, primarily the white, because the white is the small part. Now, what's going on here? Look at these, how wide these are. These are called Whistler waves, and they are 100% banging of white particles in the sound audible range. These make a sound that goes just like that. In a nuclear explosion, what you would hear and see, you'd hear, and then the white would burn down the house or whatever, and then a second later the black would come and knock the house over. That's what happens in a nuclear blast. You know, I might as well show you. All right, well, here, all I want you to do is listen. You're going to hear the Whistler wave, which I showed you before is the preceding wave that's sort of wide, and it's in the audible range. It's going to be fast. You hear it go, brrr. Listen to this. You hear that? That's the Whistler wave, audible wave, ahead of the concussive wave, which took 30 seconds or more before that reached us. All right, this is from atomcentral.com, and they got this all fitted out, and they've come up and they set it all up and everything. They're going to move the truck out of here. They've got a hardened enclosure with the camera all set up inside there that easily can withstand this, because it's coming from behind, and if it's hardened well enough, nothing's going to happen to it. But this is a normal house, and it's going to burn up, and these telephone poles will burn up, and the wiring will burn up, and nothing will move. Watch. I've got this running exceptionally slow. I have to turn the sound off. Here's what's going to happen. The bomb will go off, and we'll see a brilliant flash of light. Don't forget, they're going to take the truck out of here and all that business. And we'll see just a brilliant flash of light. I'm going to stop it. Boom, I'm stopping it. What do we see? It's just a glow, a haze. Just a haze. And then what? I stopped it again. Everything here is just smoking. There's no movement. Didn't push anything. And it's just smoking up. Nothing has moved at all. Look, the roof is smoking, the poles are smoking, the wires are smoking, everything's smoking. Metal won't. It's resistive to this invasion of electrons. And right now, all we have is the white particles. So what happened in a nuclear explosion is you got all that stuff with all the black particles in the center. So many of them, it's ready to explode all by itself. And then you lock it all tight in a really heavy-duty enclosure, and then you explode it inward, and then it just can't handle it. And then everything goes out. First, this. Burning everything, and then comes behind the black, which is the thing that has the mass. This proves this has no mass. It didn't move anything, but it's got all the energy. The fields interacting with other fields that are massless, that I can determine, they just smoke, because the fields are entangled now, and they do not want to be. They hate each other. And then comes the black, and everything goes, because the black has all the mass. So we're going to continue back here to the explosion. Nothing has moved yet. Nothing. Everything's burning up, and here comes the black. Get ready. Boom. There, I stopped. The black just hit. The black just hit. And there it goes. So That proves the white is surrounded the black, and the black has all the mass, and the white has all the gas, has all the energy. All right, so I think I've covered it pretty good, so you get a feeling for dipole electron flood theory. You're just going to have to think about every proton is made by 1,839 of these dipoles. Simple as that. When they break them, they can see them, but they see a whole bunch of other stuff too, because they don't split into exactly 1,839 little bits. They split into a chunk here, and then a bunch of the little bits. They've seen those, they just don't know what to make of them. This is the white particle, which has no mass. This didn't move. There's nothing moving here whatsoever. Not a thing moves. When the first bit of the atomic bomb goes off, it just brilliantly lights up. Now, watch this. I think I probably should, well, I know I showed it to you, but it's just going to smoke. It's just literally going to smoke. It just smokes. I'm pointing it out. The roof, the siding, the poles, the wires, everything. And then the black comes. The black pushes the white. This I can show in extreme detail from the experiments that we did between Rod Warren and myself. And this is what happens. The 1,839 of them, all the white ones went out and the black follow. See, I got 4 hands. Not too many people can do that. Boom. I do tend to carry away a little, but that's where the black is coming right after the white. The white bang, and the black follows, and the black is the one that hits, and it's all over. Roger, you are long-winded. All right, get to the point. Boom. Yes, I am. I am long-winded. But people don't, I don't know, maybe they don't like that. I like to make sure somebody understands what I'm saying, because people, oh, yeah. Now comes the black. You didn't see anything move. There's an atomic bomb blast. Nothing moved whatsoever. Almost all the combustibles are gone. Boom. Case is closed. Thank you, Roger. All right, I'm sorry. I'm going to try to finish it up quick. These protons and neutrons are 1,839 or 1,840. That's what I say of these dipole electrons, which are little tiny magnets. That's all they are. They ball together, though, tightly, and they have a black core. The white is what went out and smashed the building down, or lit the building up, just combusted it, and then the black knocked it over. When they hit theirs together, they get this, and then they get piles of trash. They see the little particles we see, but we started with that. We didn't have to start with this and end up with all this. They call it a particle zoo. So that was right from Fermilab or CERN, and this is what they found. If this is from Fermilab, these are the Fermilab pictures. Black with a colorful core around a surrounding glow, which is this right here. That's it. And the other particle is this. A glowy little bugger that has no weight. And that's exactly what they say. They can't find any weight, and the other one has all the weight. And we found them in light. Now they found them in just big chunks, and they didn't know what to make of them. We know exactly what to make of them, because they accelerated through the Venturi, exploded at the Venturi, and the white separated from the black. Now here's another shot of the same situation. All right, here we go. I know I've shown you this probably a number of times, but that's the acceleration, that's the explosion. This is a pure white explosion. The other one I'm going to show you is modified so that the Venturi allows some of the darks so that we can see that it's being pushed. You see this? This is coming through the Venturi this way. It's enough of a gap here to allow the black particles to come through along with the white. The other one, they didn't come through. It was only the white could get through. Now, and Rod Warren did these fabulous, fabulous work. Thousands of hours. Thousands. And that is the black pushing the white. Here's the house. Burn, 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 burn. See you later, house. That is what happens in a nuclear explosion. That is a nuclear explosion. It's just as simple as that. And it's in the subnuclear range. They come back together very quickly. This isn't going to go very far. This is exactly what I'm showing, is the muon, the black ball, turns into a sterile muon from a muon neutrino, which was attached to an electron neutrino, the white part, and the white part showers. Here it is. Now, in this case, you don't see that black line here pushing the white. In the first one, you can see the black line. Out here, they're reestablishing themselves, but here, there's just nothing but white. We need to harvest that right there. We could have, I think, free energy. This increases well, this is the only thing that makes energy is the white. So if you can separate the white from the black, you got lots and lots of energy. And there is 100% certainty we separated the black from the white. That's the strong nuclear force. These are inside protons and neutrons, the smallest particles that exist. This is the strong holder. Well, once you get to the first stable, well, not the first. First is the gluon, just one black and one white, which is literally heat. Then you get to the photon, which is light, and that has a complete field around it. Heat wants to attach to somebody, and the more you put into somebody, the more warm it becomes. When they leave, it gets cold, that's all. But that's only one at a time. When you have two, it bounces because it's got a field around it. That's what light is. And then we separate it, cause it to separate. And the white is 100% energy, 100% energy. I'm going to leave it at that. And hopefully Mudfossil University can somehow get funded after all of the abuse that we have suffered from dismissal by academia. I think they should support this endeavor because we want truth and reality. I think that's the purpose of education, don't you? It's not just to keep somebody occupied and just coming up with nonsense to support something that's just not true. Because they were told, don't listen to this, don't listen to that. No. And it goes on both sides. Both sides of the equation. A locked mind over here is just as bad as a locked mind over here. And there's one of them is based around some nonsense, and the other one is based around the fact they can't see what's in front of their face. It's PhD-olia. They're too smart to see. And I'm sorry, that's just a fact. I've been running into this for 15 years. Well, my whole life. But for the last 15 years, it's been extremely confrontational. And now I have won. I have won. I own education right now. I own knowledge. That's right, me. If it's true, it's true. And it is true. And it's true because of the denial in the echoing chambers of places like Yale University and every one of them, not a single one would engage because they had no answers. I own education. Mudfossil University right now is the premier school in the world. It's free. You come up, you keep looking, you keep looking, keep looking. And then go on your own and say, oh, could this be right? Could this be right? And then start looking up, start thinking, start doing experiments. It's cheap to do this stuff. This is not monumental tasks. This was done with a cell phone and a couple of cheap lasers. Construction laser, pulse. It measures distances, and that's all that is. Like $25, something like that. Of course, now with the tariffs, I don't know. All right, I love you all. Yes, we're in a new world because everybody's listened to, and they had to be peer reviewed, and that's just done. That stuff that's racketeering. That's just dismissal of truth, and it's been going on way too long. All right, so I hope And I would expect if the Trump administration wants truth, all your truth, social truth, this, everything, we want truth, we want honesty. Well, let's talk about open discussion. That's what I want. I'm not asking somebody to say, oh, yes, Roger, oh, yes, yes, yes. No. I want to say, tell me why I'm wrong. It's all I've ever asked for. All right? I do love you all. Bye.